Hi everyone. To solve this system of simultaneous linear equation using matrix method, we have to write the system using matrices. All right, so the first thing is to write the coefficient matrix multiplied to the matrix of variable, and then we equate it to the matrix of the constants. This system, therefore, in matrix form will be, we start with the coefficient matrix, where we write the coefficients. We have 4, 5, 2, 3. All right, these are the coefficients. All right, called coefficient matrix. Then the variables, we have x followed by y, and then we equate that to the constants. So this system in matrix form is written as such. Now, the method works as follows. If we call this coefficient matrix A, then if we call that coefficient matrix A, then we want to write the system as AX, where X represents the variable, equal to C, where C represents the constant matrix. So the system has this nature. So what we're looking for is to solve for this capital X. To get this X, actually we should multiply both sides by the inverse of the matrix A, knowing that the inverse of a matrix multiplied to a matrix will give us the identity matrix. Inverse of the matrix A multiplied to A will give us the identity matrix, so that we'll end up having the identity matrix, the 2 by 2 identity matrix multiplied to the variable matrix will give us this inverse multiplied to the constant matrix. Now, identity multiplied to the variable will just leave us with the variables, that is our xy, and this will just give us our solution. Now, with that at the back of our mind, let us therefore get the coefficient matrix, which is this one, get its inverse. And then we pre-multiply both sides. Remember, when we multiply from the left, we call it pre-multiplication. So we're going to pre-multiply both sides by the inverse of this coefficient matrix. So the coefficient matrix, we call it A. The coefficient matrix, we call it A. So we have to get the determinant. The determinant is product of elements in the leading diagonal minus product of elements in the alternate diagonal. So we have 12 minus 10. That gives us 2. So the determinant of this coefficient matrix is 2. The inverse is gotten from the formula 1 all over the determinant multiplied to the adjoint of that matrix. So we get 1 all over the determinant. The adjoint of that matrix is gotten from the matrix A, where we interchange the positions of elements in the leading diagonal. So this element down there goes up, that one up there comes down. So we'll have 3, and then we'll have here 4. And then we'll multiply by negative the elements in the alternate diagonal. So this gets -2, -5. This gives us the inverse of the matrix A, that coefficient matrix. Right? Now, the last thing to do is to pre-multiply both sides. We already saw from the demonstration that A inverse multiplied to A will just be the 2 by 2 identity matrix, which is 1, 0, 0, 1. And so when we pre-multiply both sides of this matrix equation, we're therefore going to obtain 1, 0, 0, 1 multiplied to x, y, to give us this inverse multiplied. This inverse here will have 3, -5, -2, 4 multiplied to the coefficient, the constants matrix. So now the identity multiplied to this will just leave us with x, y, the matrix of variable, And then we now carry out this multiplication process. We have a half into 3 multiplied to 2, 3 multiplied to 2, plus negative 5 multiplied to 0, negative 2 multiplied to 2, plus 4 multiplied to 0. And so we have this is equal to a half into 6. Negative 5 multiplied to 0 is 0. Negative 4 plus 0. And so from here we're saying xy is a half into 6, which is 3, a half into negative 4, which is negative 2. So from here, we just conclude that, we just read across that x is 3 and y is negative 2 as our solutions.